there is actually something more general that's happening here. Let me get to it. Actually, two very nice theorems here. One of them is what we call the remainder theorem. And this is really just a consequence of dividing, synthetic division, that is. Now, if you have a polynomial f of x, right? You're dividing by something like this, which is what we're doing in synthetic division. You can actually figure out the remainder easily. Not the quotient. The quotient you actually have to divide. But the remainder you can get easily. The remainder is going to be f of that a. But f, again, is our dividend. So we're dividing this by d of x, which is x minus a. The remainder is f of a. I mean, that happened in this example, right? We took this, evaluated it at -5. Remember, it has to be x minus, so -5 it would be. Get 0, which is our remainder. We went back to, see if I can get to it. Here, we have this, right? Our remainder is -4. Well, if you plugged in x minus 3, remember we divided by. So if you replace x by -3 here, excuse me, by 3, you would get -4. So this is our dividend. If you replace x by 3, you would get -4. I think that's actually what I showed next. Let me just get to it. Here it is. Right, so we calculated it directly by synthetic division. We got -4. But I'm showing you here that if you evaluate this at 3, you get the remainder. That's all I'm trying to show you. I mean, what is the quotient? The quotient q of x, you actually have to divide. And then here I just give sort of a proof, or like an outline, I guess, why the remainder theorem is true. Well, remember, if you're dividing this by x minus a, so that's what d of x is, in the division algorithm, that theorem, your remainder is going to be identically 0 or have degree less than your divisor, which is d of x. D of x here has degree 1. So this is saying that r of x, as I have here, it's either going to be identically 0 or be a polynomial of degree 0. In other words, r of x is going to be a constant. That's what we're basically saying. I'm calling that constant c. And using this equation, we can actually figure out what that constant is. Just replace x by a, as you can see. That's what I'm trying to show you. So in this case, we could figure out easily what the remainder is, almost like without dividing. That's what the remainder theorem says. And that actually gives us some more important information, taking this a step further. Namely, if this f of a happens to be 0, as in the second line here, so if this thing is 0, right, then we have this equation. And notice that x minus a is a factor of f of x. So if your polynomial, capital F, right, if capital F of a is 0, then x minus a is a factor of f of x. So you can determine if x minus a is a factor of the polynomial. You just evaluate it at a. This tells you that the other direction is true. Namely, if this were a factor, then f of a has to be 0. And really what I'm getting to is the factor theorem. This is a very nice theorem, especially with factoring. Almost like what you can do is you can determine if something is a factor without actually dividing. If you actually want to get the factorization, then you have to divide. or do some other factoring thing that we did. And I just gave some examples here. For instance, right, we have f of x is this. Okay. Well, the first question is x plus 3, which is really x minus negative 3. Remember, you want it to be x minus. Is this a factor of f here? Well, using the factor theorem, I know here I have capital F, here I have little f, but it's really the same idea. If you did little f of minus 3, so a is minus 3, right? We get 0. So that tells us, yeah, it is. So in other words, this f of x here, you can write it as x plus 3 times something else. To get that something else, you actually have to factor. Here, we did the same thing, but I changed the polynomial a bit. Instead of x squared plus, I did x squared minus, as you can see. But you can see here, though, that it's not a factor of this. Because if I replace x by negative 3, I'm not going to get 0. Okay, that's fun. Here's another example. Consider this. Well, is x minus 3 a factor of this? Well, I replace x by 3 here, right? As you can see, I get 0, so the answer should be yes. I guess you could check also, or, just to get the actual factorization, you divide, and that's what I'm doing here. So again, I didn't write all the details in this one. As you can see, what I did do, okay, was this. I did the synthetic division. So we have 3, the 1 comes down. 3 times 1, that's 3. Negative 1 and 3 is 2, right? I multiply. I put it 1 column to the right, 1 row up. I add to get 2. 3 times 2 is 6. Negative 14 and 6, that's negative 8, right? 3 times negative 8 is negative 24. 24 and negative 24 is 0. So yeah, we do get 0 as a remainder. In other words, we can write this as x minus 3 times the quotient. What's the quotient? Remember, this is degree 3, so the quotient's degree 2. We have x squared plus 2x minus 8. And the remainder is 0, so we just have this. I mean, if you wanted to keep going, you could. I mean, this thing you can actually factor using, what do you call it, I guess the AC method. Although since the coefficient here is 1, you would just need 2 numbers whose product is negative 8, but the sum is 2. I'm guessing 4 and negative 2 would do it. But you can factor that easily. All right, I got to stop. I'm out of time. All right, I'm out of time, so